Yeah, that's true.
Bring your lunch, man.
So what was the answer you got? Wait, let me ask people one at a time. Let's just pick people at random. Jake? So what was the last 2 digits for last night's homework?
Oh, 24.
Okay, that's impossible. Because wasn't it an odd number?
It's 7, yeah.
27.
No, it's the last.
Okay, what was the homework problem?
37 to the 73.
37 to the 73.
How can that be?
This obviously.
Okay, just, no,
There's
it's not.
98 more
Okay,
numbers.
Kanashiro? Just look it up on your homework.
Oh yeah, good.
Okay, stop doing it. Hong.
I didn't do it. I did it as 8, and I tried to come up with the board, so I did.
What? Math team lieutenant?
But I didn't do number 8 though.
It's
Transparency.
Learner.
17.
Is that what you got?
I got 97.
What are we gonna do it then?
I got the same part right.
Wait, I got 97 too.
I think it's 90.
You got 97?
I plugged it into Wolfram Alpha, but
What? We're not doing Wolfram Alpha. Okay, just for that song, get a calculator so that we can.
yeah, it's
We can just do
97.
this.
Yeah, I got 97.
So 97 then?
Yeah.
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 Okay. Just the same time, this is, I don't know for sure, but this is what Wolfram Alpha said.
Yeah. And I also did it and I got 97.
Okay. We are fairly confident that this is the answer. Okay, I'm telling you right now, this problem is on the test, but you're not gonna have a calculator now. Oh boy. Okay, now, today we do indirect proof. Now, do you guys remember the concept of indirect proof when we did logic?
No.
Okay, let's do an indirect proof. Okay, let's do a logic. This is a good review of logic, in fact. Let's do the law of syllogism. You guys remember that?
Oh.
If P, then Q. If Q, then R. Therefore,
P implies R.
if P, then R, right? This is called the law of syllogism. Now, we can prove that this is a valid argument by making a truth table. Remember doing that?
Yeah.
Okay, but we're going to do an indirect proof. So, in order for this argument to be valid, if these 2 statements are true, then this has to be true. This is the conclusion, yeah? So an indirect proof looks like this. Suppose that this conclusion here is false. I'm just going to put capital F for false. So that's always the first step in an indirect proof. You suppose what you're trying to prove is true is false. And then what you're going to do is you're going to get a contradiction. Okay? If you get a contradiction, then that means this statement was actually true, and that proves it. That's why you're proving it indirectly. Okay, so let's see how much logic, and you know I'm going to call on you a lot.
Let's go.
And you. Okay, what kind of statement is this? P implies R?
P is 2R.
No, it's called a conditional statement. Weren't you in logic this year?
Yes.
Oh my God.
Last week.
Okay, now, if a conditional statement is false, what can we conclude from that? Yeah, this is true and that's false, because that's the only time a conditional statement is false. Hope you guys remember some logic. So you can say something like, so P is true and R is false. And then what you do is you take this up here until you get a contradiction. Okay, so now remember, the key to doing this is these 2 are assumed to be true. So if P is true, and this is a true statement right here, then what can you say? Q has to be true as well, right? Because remember, the only time a conditional statement is false is when the first one is true and the second one's false, right? But then this is a true statement. But now we know Q is true, and if this whole statement here is true, doesn't that mean R is true?
Yes.
So do you see a contradiction?
Yeah.
Yeah, R, we just said R is false here, but over here it says R is true. That's your contradiction.
Yes.
That's the hardest part of an indirect proof. You gotta come up with a contradiction. So there's your contradiction. So Then you say contradiction was, this is how we did it in logic. Contradiction, and that's your whole goal of an indirect proof. And then the reason is R cannot be both true and false. Therefore, the argument is valid. So we're going to use the same reasoning. Now, I'm going to do these three problems. This is your homework, and we're going to do all three on the board. And I'm going to tell you, one of them will be on the test. There's only going to be one indirect proof. It's going to be one of those. You just have to be able to regurgitate. Okay, so let's start with the first one. So we go through these three proofs, and we go to lunch early. Number 9, if, you're on camera here. I'm going to show that to the administration. Dr. Chin, take a look at this. What do you think? If a squared is even, then a is even. Now, this is assuming a is an integer now. So basically a and a squared are integers. Okay, so this is a conditional statement. So what's always the first part of an indirect proof? We're going to suppose that this is false, but it's a conditional statement. So suppose, I guess I gotta write it again. A squared is even, implies a is even, is false. So what does that mean? If a conditional statement is false, that means what? So a squared is even is true, and a is even is false, right? Because that's the only time a conditional statement is false. Okay, so what we gotta do is try to come up with a contradiction. Actually, we didn't even need to do that, but that's okay. Okay, so how do you want to work this? We have to get a contradiction here.
2K.
A is odd, so 2K plus 1.
Yeah.
Okay, so if A is even is false, that means that A is odd then, right? So that means A is equal to 2K plus 1 for some integer K. And then over here, we're going to prove something about A squared. So squaring both sides, A squared is equal to 4K squared plus 4K plus 1, which is equal to 2 times 2K squared plus 2K plus 1.
A squared is odd.
So A squared is odd, and there's your contradiction, right? Because over here it says A squared is even is true. So therefore, that statement is true. Now you might think, why is this like, this is an easy one? Yeah, that's because we're going to use it in the next one. So you can probably guess this one is not going to be on the test. It's going to be either 10 or 11. This one is just to set up number 10. Now this one is one of the more, what did I say yesterday? One of the most, not inspirational, useful proofs in the history of mathematics. The square root of 2 is irrational. Okay, who proved this? Anybody want to guess? Okay, who's on the science boat? This is the kind of questions they ask, right? Who proved that the square root of 2 is irrational? No, Euclid. I fooled you on that one. Okay, so suppose the square root of 2 is rational. Now, you guys know what a rational number is, yeah? It's a number that can be written as an integer over an integer. So, square root of 2 is equal to, what letters you want to use? A over B? Where A and B are integers. And here's the key to the whole proof. And A over B is in lowest terms. This is the most important part of the proof. That's where we're going to get our contradiction there. Okay, so now you start working with this until you get a contradiction. Because anytime you have a fraction, you can always put it in lowest terms, right? Okay, so what am I going to do with this? Square both sides. So 2 is equal to A squared over B squared. Which means A squared is equal to 2B squared. So therefore, a squared is even, right? Because it's equal to 2 times an integer. But what did we just prove? If a squared is even, then a is even, right? That's why we did this thing first. Okay, now, if a is an even number, then what does that mean? A is equal to 2k for some integer k. Okay, now what I'm gonna do with that?
Prove B is even.
Huh? Take this
Plug it
and
into-
plug it into here. So, if this is a, what is a squared? 4k squared is equal to 2b squared. Therefore, b squared is equal to 2k squared. Therefore, b squared is even. And then from this thing, b is even. Does anybody see a contradiction?
It's not in lowest term.
Yeah, because if a is even and b is even, then a over b cannot be in lowest terms.
Yeah.
That's the contradiction, so. Contradiction. So therefore, the square root of 2 is irrational. So that's kind of a clever thing, right? In ancient Greece, they used to do these kinds of proofs. Okay, the next one. Okay, the next one was also proved by Euclid, that there is an infinite number of prime numbers. Now, you guys kind of just think nothing of it, but think about it. How would you prove something like that?
Finite.
You do an indirect proof. So, number 11, there are infinitely, how do you spell it? Infinitely many prime numbers. Or we could just say primes. So the first step is suppose, what?
Find the finite.
That there's a finite number of prime numbers. So suppose that there is a finite number of primes. Well, this guy Euclid, he's pretty clever. So if there's a finite number of primes, doesn't that mean there's a biggest one then? There has to be a biggest one. So there must be a largest prime. And what do you want to call this largest prime? Okay, P then. Now consider this number. Consider the number 2 times 3 times 5 times 7. In other words, multiply all the prime numbers together, all the way up to P, and then add 1 to it. In fact, what do we call, what do you want to call this number? Consider the number,
Yes.
huh?
Oh, why do you add one?
Shade.
No, well, you see. You'll see why we have 1. What letter do you want to call this so I don't have to keep writing this?
K.
K. I don't like it, but we'll do it. Okay, consider the number k, which is equal to the product of all the prime numbers plus 1. Now, how do you determine if a number is prime?
One in it.
Okay, so, is this number here divisible by 2? No, because when you divide it by 2, you get 1 remainder, right? Because 2 goes into this, but then you're going to have 1 left over, right? K is not divisible by 2. What about 3? No, because when you divide this number by 3, you get 1 left over.
Oh my
So
God.
K is not divisible by 2 or 3. What about 5?
No.
What about 7?
No.
What about all the way up to P?
No.
No, so if a number is not divisible by the prime numbers, then what can you say?
Oh.
This number has to be prime. So K must be prime.
Oh.
That's so
yeah.
Now what's the contradiction?
Bigger.
This number here is bigger than P. So hence, P is bigger than K, and that's a contradiction. Contradiction. Therefore, there's an infinite number of prime numbers.
Oh my God.
Oh, wow.
Isn't that pretty cool? I mean, just to think of something like that, yeah?
That's
Yeah, it's mind blowing.
I know.
Wait, so that's how you find, that's always true? So if you wanna just, like, if you wanna think of like any prime number, you just have to multiply the previous prime number and then just plus one?
Yeah, but there's an infinite number of prime numbers.
No, but like, like if you wanna,
Yeah, so if you wanna come up with a big number that you know is not prime, then just multiply all the prime, just,
but
no, wait, I'm not done. No. Okay, one more, 23, add one,
you can't like take out, you have to input every single one of them,
huh?
right? You can't just take out 13.
No, because
It could be the different way.
Oh.
No, you're gonna get arrested.
so, this number here would be prime then, right?
Yeah.
Because if you divide it by any of these prime numbers, you're gonna get one left over.
Never need this.
Well, yeah, these are like two of the most famous proofs in mathematics right there. Okay, so tonight's homework is do the 3, but I did it. So what do you think you're gonna do?
Review
Take
the
picture.
together and view
You're
me.
gonna be able to repeat it?
Yes.
Well, since we have so much time today, maybe now is, yeah, let's do it. Because it's actually gonna take a while to discuss tomorrow's one. So since we have time, let's actually prove that 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared forever equals pi squared over 6.
Oh.
Okay, this problem is also gonna be on the test, you just have to regurgitate it. Because I tried to do something else last year and then, no, it was a nightmare. So, as long as you can repeat it, it'll be good enough. So we're gonna prove sigma on n equal 1, wasn't this on a math team shirt?
Yeah.
Yeah.
I don't know, when was this?
Last week.
1 over n squared
What?
equals pi squared over 6? When? What?
Last week,
You're
right?
a funny boy.
No, on the math
On
team
the
t-shirt.
shirt.
We don't even have a shirt
We
this
don't even
year.
have a shirt this year.
What are you talking about?
They're all black. They're all-
Wait, I don't think it was this one. I think it was.
No, it was like maybe 3 years when you were a freshman, maybe?
When Chenny.
Oh yeah, no, it was definitely my brother's year. Yeah.
1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus ... is equal to pi squared over 6. How do you prove that? Well, Euler came up with a pretty good, now hopefully I can remember this. Okay, so what Euler did is he said, oh, consider the power series for sine x over x. Okay, what is the power series for sine? You guys remember that at least? Come on, you guys all got 5s on the AP exam, right?
X minus x cubed over 3 factorial.
Oh, very good. So sine x is equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. Come on, you guys did it 2 years, PCH and BC.
Yes.
Okay, so what is the power series for sine x over x?
One.
1 minus x squared over 3 factorial plus x to the 4th over 5 factorial minus x to the 6th over 7 factorial plus ... Okay, now I gotta think. Gotta think like how Euler thought. What are the, okay, so when will this be equal to 0? When is sine equal to 0? 0, pi, 2 pi, 3 pi, plus or minus, right? Plus or minus pi, plus or minus 2 pi, plus or minus 3 pi. But when you divide it by x, then you take away the 0 then, yeah? So considering the zeros of this function here, which is this must be equal to, okay, I hope I get this right. 1 minus, is it x over pi or pi over x? No, x over pi. 1 plus x over pi. 1 minus x over 2 pi. 1 plus x over, you get it? 1 minus x over 4 pi times 1 plus x over 4 pi, ... forever. Right? Because the zeros of this function here, like we said, are plus or minus pi, plus or minus 2 pi, plus or minus 3 pi, and so forth, right? But not 0, because you can't divide by 0, right? So what are the zeros of this function?
Pi.
Pi, plus or minus pi, plus or minus 2 pi, plus or minus 4 pi, and so forth. Okay, so what we need to do, and here's the hard part, I hope I got this right. We gotta multiply this out
Huh? Until where though?
forever. Okay, I'll multiply the first two, you get 1 minus x squared over pi squared, right? Multiply the next two, you get 1 minus x squared over 4 pi squared. 1 minus x squared over 9,
Wait, you still.
yeah, I skipped one, fool. This should be a 3. 9 pi squared, 1 minus x squared over 16 pi squared, dot, 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 forever. Right? Okay, now, multiply out. Can you see where this is going?
Yeah.
Because look right there. That's x squared over 6. Okay, never mind, just, okay, how the heck do we multiply this out? What do we do? Okay, 1, right? Okay, and then plus, okay, now there's gonna be a term with x squared in it, right?
Yeah.
What's the coefficient of x squared gonna be? Like, how do you get an x squared term out of here? Well, one of them is gonna be this one right here, when you multiply 1 times this, right?
It's just all
Yeah, so everything, so minus 1 over pi squared,
the, yeah. Minus 1 over 4 pi.
and then what about this one here?
Oh.
Minus 1 over 4 pi squared,
Yeah.
and then from that one, gonna be minus 1 over 9 pi squared, minus 1 over 16 pi squared, minus dot, dot, dot. Okay, so equating the coefficients, then shouldn't, here, this is the x squared term on the left side, right? This is the x squared term on the right side, so equating the coefficient, then shouldn't negative 1 over 3 factorial, which is 1 over 6, equal to negative 1 over pi squared minus 1 over 4 pi squared minus 1 over 9 pi squared minus dot, dot, dot.
Yeah.
Whoa.
You guys see it yet? Not yet?
Multiply by negative.
Okay, so negative 1, 6 equals, what can I factor out from this? A negative 1 over pi squared. What's left?
1.
1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus dot, dot, dot. So therefore, 1 over 1 squared plus 1, yeah, I did it right. 3 squared plus dot, dot, dot is equal to pi squared over 6. Boom. Euler.
Oh.
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 Okay, so what I did last year is I kind of extended it. So so knowing what we did here, no one even came close to the answer. So knowing what we did here, what is 1 over 1 to the 4th plus 1 over 2 to the 4th plus 1 over 3 to the 4th plus dot, dot, dot? What is that equal to? So what do you think you would have to do? You would have to get the coefficient of x to the 4th and set it equal to 1 over 5 factorial. But no one even came close last year. Yeah, so you gotta figure out, okay, how do you get an x to the 4th term when you multiply these two together, right? And then when you multiply these two, those two, and then these two, these two. And you just keep multiplying and then you'll see a pattern, yeah? Anyway, that's what you would have to do to get it. So that's like the Euler technique there. But I decided I'm not gonna do that anymore because no one even came close. So as long as you can repeat this and no faking.
What do you mean?
If I see any sign of a fake, I'm gonna take off triple. It'll be minus 30. Anyway, you guys have your HV prime with you? You guys, so if you put it into CAS mode, I think your calculator will give you the answer. So here, punch this in on your calculator. So what would that be? sigma n equal 1 to infinity 1 over n to the fourth, yeah? Sure, but you gotta be in CAS mode. Do you even have your HB prime? What about the app? Come on, you gotta do something. This is not second semester yet. See, this is why we don't like to have multivariable second semester. Except you started early.
How do you get infinity on?
What? No, it's not. I think it had something to do with 324. Well, let me see.
How are you supposed to get like the infinity at the top?
There's an infinity button on there, I think. Try looking.
There's an infinity button.
Yeah, there's an infinity button.
Can I use that for just regular calculation?
Is there like a what do you call a list of?
Oh, I see it. It's in the 9.
Oh, there.
Oh my god.
Oh, pi to the fourth over 90.
Pi to the fourth over 90.
What is it?
It's gonna-
Okay.
So this is equal to pi to the fourth over 90. Well, if I remember last year, I don't think anybody even got an answer. Who was in MVC last year? Kim. Oh, Kim actually worked on it for like, because I think we had an extended period for the test, and I think she worked on it for like an hour.
Did Takao get it?
Who?
Takao.
Takao, come on. Takao, if you're watching this, come on. Where did he go?
Oh,
Oh, wait. He went to a community college
yeah.
in California.
Transfer.
In California.
Yeah.
That's a bad place to be right now.
But wait, is he there?
No.
Where did he transfer from?
Oh, I don't know.
Oh, he just went
No,
there.
He applied there. Yeah.
Oh,
He's
well,
getting
you-
older now.
community college, I don't think you really need to apply, right?
Yeah, you don't.
I think you can just,
Yeah, just
well, not
show
show
up.
up, but you gotta register.
Yeah.
Anyway, so you could, because actually, when I gave this problem, wait, let me think. What was we had the really good math team captains then. No, 2 of them were juniors even,
What?
1999.
Oh, bro.
So 1999, I gave the problem, almost all the whole class got it. In fact, that was the year, you guys know the Mandelbrot competition?
Yeah.
They actually stopped it this year, but we actually were number 6 in the nation that year.
Oh,
Was
Well,
it frisbee?
do you still remember their names?
Yep,
Would you
Tanner Fall
remember our
and
names?
Jason Young. Those are the captains, but then there are others. That was a really smart year. Francis Lamb.
Are we a smart year?
Oh yeah,
we're pretty
Will you remember me, Mr. First?
of course, Daniel.
I'll take it.
All right, so no, I'm not gonna give you that, but I will give you this. So, okay, so the next time we need to learn, after we show you this, I gotta show you the Chinese remainder theorem.
Oh, yes.
Okay, so I'm just gonna show you the problem and maybe you can kind of think about it. Hey, did you know in Math League, back 20-something years ago, we used to have what they call this extracurricular event that would rotate every year. So like one year would be number theory, and then we had non-Euclidean geometry, we had statistics, but now statistics is actually part of it now. Group theory. Yeah, so every year there would be an extracurricular, and one of them was number theory. And you could have problems that included the Chinese remainder theorem. Anybody Chinese here? Put your hands up.
Sian is Mongolian.
Mongolian.
Anyway, you can use the Chinese remainder theorem to solve a problem like this. I remember one year we had this and they said, Mr. Park, you don't need to use the Chinese remainder theorem, and they just figure it out. So I have a number of eggs in a basket. I'm not going to tell you how many there are, okay? However, if you divide it by 2, how am I going to write this? If you divide it by 2, then there's 1 remainder. If you divide it by 3, there's 1 remainder. You divide it by 5, there's 2 remainder. You divide it by 7, there's 4 remainder. If you divide it by 11, there's 5 remainder. What's the smallest number of eggs that I could have in my basket? So from this, it has to be an odd number, right?
Yeah.
And so I guess you could figure it out.
2 times 3 times 5 times 7 times 5, and then just do all of them. And
How do you solve it?
that's a
No,
Chinese
first
remainder
one.
theorem.
No, so the Chinese remainder theorem is like an algorithm so that you can figure this out.
But then you would have to subtract the product of 2, 3, 5, 7 until you get the lowest one.
Yeah, you take a mod like
Yeah,
All
you
of
take
them.
a mod that big.
2 times 3 times 5 times 7 times 8.
So wait, you guys think about, wait, let me see if I even have it on here. Because before I used to have it on here.
Here, like 2 times 3 times 5 times 7 times 5, and then
Let's scroll down. Oh, there it is, the Chinese remainder theorem.
Yeah, it's like
There it is.
and then like 2 times 3 times 5 times.
Okay, we're not gonna go through it now, but this problem's gonna be on the test too.
That's like a big number.
All I will do is I'll just change some numbers around, change it to a 2, a 4, a 6, and an 8 or something. And then maybe I'll add a 13 there. Hey, don't get upset. You get upset too easily. Oh, who's the counselor? Who's your counselor? Higashihara?
80.
Who?
80.
no Asato.
Oh, Sato.
Oh, Sato. Hmm.
No.
Maybe she can do some electrotherapy. All right. So I think next time will be the last lecture of the whole year then.
Let's go.
Okay, so no, you know what? I think I think the Chinese remainder theorem, we're gonna have to save it for next week. Wait, how many times more do I see you this week? Just tomorrow, right?
Yeah.
So tomorrow we do mathematical. Have you guys even heard of mathematical induction?
Yeah.
Reduction.
Just now.
We used to actually do that in PCH. We used to do all of this in PCH, but we know what happens, right?
Induction to fire thing. Are you kidding?
Hey, PCH used to contain so much stuff. We even did statistics in there too.
Easy.
No, but that's when we used to meet every single day. Every single class meets every single day.
Well, isn't it shorter time?
Yeah, like 40 minutes, but
Oh.
you can still get a lot done. But can't do that anymore. We used to even do rotation of axes. You guys know what that is?
And you use matrices to do
Yeah, that's actually a matrix. So here, you remember in PCH when we graphed tilted ellipses?
Yeah.
Well, actually with the TI, what HP prime,
that?
you have advanced graphing. Because remember, okay, here, you have an equation like this: 2x squared plus 3xy plus 4y squared minus 5x minus 6y minus 1 equals 0. This is going to be a tilted ellipse. So before in PCH, I think when I taught you guys, did you guys have HP primes back then?
Yeah.
But I didn't know about the advanced graphing. What we would do is we would use the quadratic formula to solve for y. So you would get something plus or minus the square root of something all over 2a something. And then you would graph one with the plus, one with the minus. So the plus one would graph the upper half, lower half, and you get the whole thing. Do you remember that?
Yeah.
Okay, but now with advanced graphing, if you go to the advanced graphing app, you just punch it in like this and then your calculator just graphs it. Tilted ellipse. Okay, but back in the old days, before there was even calculators, graphing calculators, you know how we used to graph this? We would rotate the axes. This used to be a PCH. See, so if the x and y axes are like this, what we would do is we would rotate it
Using like a
like this. We would rotate the axes, so you get a new x-axis and a new y-axis. And so now, see how the major axis and the minor axis are perpendicular parallel to the new axes?
Oh, did you have to use parametric?
No.
It's like a.
So the key is, You can rotate the axis just enough so that it would be parallel to the major axis or the minor axis. And you know what that angle is? Let's see if I can remember this. This is 20-something. Tangent 2 theta equal b over a minus c. So for this problem, it will be 3 over 2 minus 4, negative 3 halves. So if tangent 2 theta is negative 3 halves, then that's the exact angle you rotated so that in the new coordinate system. See, because this term kind of screws everything up, right? You can't complete the square, yeah? But if you rotate it just enough, then the new equation will not have this term, and then you can complete the square and put it in standard form. That was a pain. It took like a whole page of work. But now with graphing calculator and the advanced graphing app, just punch it in, boom, I think graphs it for you. So that's an ancient relic that I don't think we'll ever go back to. But that's what we had to do in the old days. That was kind of fun if you liked algebra. In fact, some of you program computers? No. So, okay, here, let's see if my memory is good. The rotation formulas were, I think, x equal x prime cosine theta minus y prime sine theta. And then y equal, gosh, x prime sine theta plus y prime cosine. I don't know, it's something like this. I think I'm remembering that wrong. That's the relationship between the original coordinates and the new coordinate system. Thank you for pretending to be amused.
Mr. Park.
Yes.
599.
Is it?
No, wait, is it? Yeah.
I think so.
No, wait.
No, you can't be using calculator though. Chinese, the Chinese back in.
No, we just checked.
Wait, the 5 doesn't even. Oh my
Three
God.
doesn't
work.
Okay, somebody remember this problem, and we're gonna do it,
Oh,
and then we'll see if we get 599.
it's
No,
not
three,
599.
We see how good Kaneshiro, Daniel Kaneshiro is.
The 5 does not work.
Somebody wanna take a picture? You take a picture of that.
I believe they are.
That's gonna be our example when we do the Chinese remainder theorem. How did you come up with that?
2.
Oh, when I was talking about rotations, I was doing it, Mr. Parker.
No, I did it before.
Okay, let's go to lunch.
No, the first digit has to be 7. The one digit has to be 7.